Thank you everyone for attending, and welcome to another one of CAE Associates Ansys e-learning series. My name is Eric Stamper, and today I'll be covering simulating interference fits. So to start off with a quick introduction, CAE Associates is an engineering consulting firm in Middlebury, Connecticut. We're specializing in finite element analysis and computational fluid dynamics. We've been an Ansys channel partner since 1985 and have developed our Ansys e-learning series to help you maximize your software investment. So please visit our webpage too, which includes an extensive resource library with over 250 items and counting, and it's pretty easily searchable. We also invite you to visit our Engineering Advantage blog, where we share insights from our many years of experience performing engineering analysis. And CAE Associates offers an extensive scheduled Ansys courses taught at our Middlebury office. And if you need help deciding on the best courses to take for your application, you can just visit our CAE University page. And of course, for a complete library of our e-learning recordings, they're available for viewing in our resource library and also on our YouTube channel. And if you are a licensed professional engineer in New Jersey or New York and you wish to obtain some PE credit for your attendance, we ask that you attend the entire webinar and complete a short survey at the end, which we'll email you at the end. And everyone has also been muted. If you have any questions during the presentation, please submit them through the chat window. And if we have time at the end, we'll go through them or we'll follow up with you through email. So as I mentioned, today's e-learning is on interference fits, sometimes called shrink fits, press fits. All really means the same thing. And to start off with, just to give everyone a couple practical or real-life examples where you have interference fits to start off with. So some examples are your car engine block. Now, there's many components on there that have an interference fit. And the example that's shown here is you have the engine block, and then you're putting in a sleeve that has a higher grade material in it where the pistons go. And if these were both sitting at room temp, this sleeve wouldn't fit in the engine block because it has a larger diameter than the size of this hole. So the way that these get assembled, you'd heat up the engine block, cool down the sleeve so that they thermally contract and grow, and then you'd be able to fit those together. And then when they reach room temperature, they'll induce an interference fit, and they'll be held in place with friction. So this type of assembly is also done on other components in the engine, like valve seats and guides and other things. But that's what we're talking about when modeling interference fits. We're talking about these types of problems. And then another example is on jet engines. A lot of the flanges that hold the rotors together have snap seals in them. There's also this component that's blown up here as a seal. And this would be assembled with an interference fit as well. It might be cooled down, the rotors heated up to get these to fit together, and then they're just held in place afterwards. So a couple examples of some interference fits. And then at the end of this presentation, I'll talk about this situation, which this isn't an interference fit problem, but essentially the way to model this is the same. Where in this case is it's a seal that's being compressed down. You could model the simulation process by squeezing that down, or you could just start off where this is going to be in the closed position, I guess. So you could start off with some interference initially in the model that way and resolve out the interference. So really the analysis technique is the same, can be the same for this type of problem as well. So I just mentioned resolving some interference. What does that mean? Well, really in real life, when bodies or parts come in and out of contact, they don't penetrate each other. The surface of one will touch the surface of another. But if we're dealing with contact in Ansys and using a penalty-based algorithm, they will interpenetrate each other, and that might be at the end of the analysis, and that's non-physical. So this is generally very important in interference fit problems. So you have one part that comes into contact with another body, and at the end of the analysis, there's some physical penetration in there, which is non-physical. So that's what we're talking about, resolving out this initial penetration at the end of the analysis, or how to set up an interference fit problem that has this in the beginning. And just quickly why this happens with a penalty-based method. We need a way to establish compatibility between the two surfaces, or we need a way for the load to be transmitted between two surfaces. So with the penalty algorithm, when one contact surface penetrates through a target segment, and you do have some physical penetration that results in the model because of that, a spring will get turned on when there's some penetration, and that spring has some stiffness. And because of that displacement, we have some restoring force that gets applied to the contact surface to push this back out to the surface. But as long as there's penetration in the model, then the spring is active and these are able to talk to each other, transmit load. So since this is non-physical, like we said before, we want to try to reduce this. One of the ways to reduce the penetration is to increase the contact stiffness. So in doing that, it's generally a more accurate answer, but it's typically more difficult to get to converge. So we're going to be talking about penetration here, but the way to reduce that is to increase contact stiffness with a penalty method. So if we just look at a problem here and where penetration is important and, cases where it might not be important. So let's just say, for instance, we have a couple blocks that we're modeling here. And those two blocks, we put those in a vise and then just crank up on the vise and displace at 0.1, some amount of displacement. So we start off and then squeeze these together. We could simulate this, and we'd have some contact in between these two parts. So this is one way we could set up and solve this problem. And then a second way we could solve this problem is, so this displacement here is at the same level. So this vise is already cranked up to where it was in this example, but we cool these blocks down, thermally contract them, make them small, and then fit in nicely in the vise. And then when they heat back up, they induce some load in the model. Well, we could simulate that process too with thermal expansion, but we could also say just keep these two cubes at room temperature. Those are the original size. Put those in the vise, and we have some physical geometric penetration between these, that 0.1. So if we went and solved this analysis, the starting position is there's some initial interference, and at the end of the analysis, these would be line on line and inducing that load in the problem. And then last case here, again with contact, we, instead of putting on a displacement on the top like we did in this first case, we apply a pressure, and that pressure is equivalent to what it would take to displace 0.1 inches. So in all these cases, we're just modeling the same thing but a little bit differently. So if our goal is to predict the stress in all three of these cases, which of these cases would be sensitive to having that resulting penetration at the end of the analysis? So we'll look at that. And if we ran this first problem, displaced it down from the original location down, and then if the contact here had a 0 penetration at the end of the analysis, then we'd get some stress. We'd also get the same exact answer as this case right here, where we started off both of these fixed. We had some initial penetration, and then if that went to 0, these would be equal to each other. And then this case with the pressure, well, the stress is just force over the area, so it doesn't really matter where this model ends up lying or how much penetration there is at the end, because the stress is always going to be the same regardless. But if you're looking at displacement, obviously that's going to be a different answer between the two, so maybe you need to minimize penetration there. But if we're looking at just stress, this case is not going to be sensitive at all to penetration, whereas these two will be directly sensitive to the residual penetration, because that's the only mechanism to get the load in the model in this case, right? We're just holding it fixed, and it goes from that 0.1 to 0. That's going to induce all the load in here. So you have to decide when it's going to be important for you. So if we looked at this middle case here, where we start off with an initial interference fit problems are generally always sensitive to that resulting penetration that you have at the end of your analysis. So it's your job to make sure that you understand that and know when your analysis is going to be sensitive to that. So one of the ways you can do this is to just increase the contact normal stiffness for a penalty method. Again, that will reduce that non-physical penetration and give you more accurate results. And you could run a couple different cases and see how sensitive your results are to that. So I made this chart. This is from that previous example on the other slide. And if we look here, this is the normalized stress. It goes up to a value of 1, so that's the ideal solution, or the Hankout theoretical solution, what it should be. And if we look at this red line, which is the penetration that results in the model, when the penetration is very, very small down here, this is the penetration number, essentially 0, we get the full load going in the model, as we might expect. And then as we leave some resulting penetration at the end of the analysis, we're not putting as much load in the model, so our stress is much lower than what it should be, and that goes down pretty quickly as the penetration starts to get larger in there. So you can see that this gets pretty sensitive to the resulting penetration that we allow. And think about this in the opposite way, the penalty stiffness. As you increase the stiffness, the contact normal stiffness, as a result of doing that, you're reducing the penetration, so then the stresses go up closer to what they should be, right? So looking at a value of 1 here for the normal stiffness, that's the default of what Ansys calculates for this particular problem we've been looking at, and that's 97.5% of the value that we would expect. So if you can live with that error in your analysis, then maybe you don't worry about increasing the contact stiffness further, but if that's too much error, then increase that contact stiffness, reduce the penetration, and then you'll get a much more accurate result. So you can see here just taking the default from 1 to 10, bumping up the stiffness in order of magnitude, maybe that's what we're looking for our error. And it just shows, again, that you can't always rely on all the defaults in Ansys to give you the accurate answer that you're looking for. It's your job to make sure you're you're trying to understand what's driving the stress and, reducing this thing that's an artifact of the penalty method. It's non-physical. So, and then, of course, there's a pure Lagrange method, which doesn't have a contact stiffness associated with it. And that's always a value of what it needs to be, because that is essentially 0 penetrations allowed in that contact formulation. So those are just a few things, just to kind of emphasize what's important in terms of penetration, contact stiffness. Let's look at maybe a more realistic problem now. So this is a case where we're modeling. This could be a shaft with a bearing or a pin and a plate, however you want to look at it. But we're going to model this in 2D with a quarter symmetry model. And we're going to model the interference fit. So maybe heat up that bearing, slide down the shaft, and it cools down. And that's the interference fit problem we're talking about. We can model this a couple different ways, one with contact offset and one with geometric penetration to get in that initial interference. And since we're looking at stress results and things like that, we'll also look at the difference in mesh and then some contact detection methods for getting more accurate results at that interface. So these are some of the things we'll talk about next in this problem, and we'll show it in Workbench in a second. So some of the settings that we're going to be talking about and I've just talked about, under the contact pair is where most of these things are. The normal stiffness, we said increase that if you want to reduce the penetration. So we talked about that guy already. And then we'll talk about the interference fit or contact offset and what the pinball region is, and then some detection and element order we'll come to at the end. So, like I said, you can model the interference fit problem here 2 different ways. One way would be to model the pin and the hole to be line on line. That's the geometry is modeled that way. And if you did that, if you ran that analysis, there'd be no load that gets developed in the model initially, because everything's line on line. There's no mechanism to put load in. So what you could do is, for a contact pair that goes between these 2 bodies, the contact surface, you can offset it mathematically some contact normal amount. And that's the value that you'd put in here for the offset. And then that's just going to physically move the contact surface off the face of the pin. And then when we solve this problem, that plate, this brown piece, is going to have to, its edge is going to have to come up to this dotted line. And that's where the contact's going to occur. So we're inducing the interference fit just by offsetting the contact surface. Second way we could do this is to model the 2 geometries geometrically as they might be sitting at room temp, right? They have some interference fit. You would heat up this brown part so it thermally expands, and you put them together, and then they load up. So at the end of the analysis, these 2 edges would be line on line with each other. And this is more realistic, right, because that's the geometry that you have in real life. This second case here is a little less realistic because the pin is really at a smaller diameter that you've modeled it, but you're trying to make it be larger with a contact offset. So we can look at the differences between these 2 results in a second. But those are 2 ways we can model an interference fit. And now, if we do that, when we have an interference fit problem, this red body is the contact side, and then this yellow guy over here is the target. So these are the interference. This is the interference that we have initially in the analysis. Now, there's something called a pinball radius, and all that is it's a contact detection zone. So all that we're looking for here is that this target segment, the target surface, goes through that contact detection zone, or the pinball radius. In order for that to happen, you just need to make that pinball radius at least as large, or maybe a little bit larger, than the interference that you have initially. And that way, at the start of the analysis, this contact surface through here realizes that it is penetrated to this target segment, and at the end of the analysis, it needs to move up to this surface. So that's just something that you just need to account for and look at. So just make it at least as much as the interference, and then that contact will get detected. So then for this problem, good idea just to do a hand calc to see what our stresses should be, and we see that we should be looking for something around 66.6 repeating KSI. So keep that in mind when we look at the model here. So this is the workbench model for this pin in the hole, and we're starting off with this being modeled line on line with a contact pair. And if we look at this contact pair, what we've done is we've included an offset, so that means that this blue line that's through here is going to be offset some amount by that 5,000. So this contact surface is really going up through the model through here, and we made the pinball radius larger than that. That way it'll get initially detected. And if we looked at the results that we get when we solve this, we see that we're getting like 67.7 KSI. So we're close. That's about a percent error from our hand calc, so that's not too bad. And if we looked at deflection and zoom in down here a little bit more, we'll see that there is a gap. This is set to true scale, and you see a physical gap between these two bodies, and it's set to 5,000. Right? That is equivalent to, on this contact pair, the offset amount that we put in. So we can see that we did mathematically take that contact surface, offset it from the face, and we see that there is that gap, but it's transmitting load through there. So that's just an artifact of what we've done. We've just moved the contact surface off the face of those elements. And if we also look at the results, they're pretty nice and uniform around the circumference. So that this is not a reasonable, I would say, a reasonable answer to the problem. We can model this same exact thing one other way with a geometric interference. I have a parameter set up here that will allow me to change this geometry. So right now, we just ran this again. It was line on line. So I'm going to change the pin diameter and make it larger, so that way it's initially interfering, so the geometry is overlapped. And we see that right there. Now we have a geometric penetration between these two. And if we do this, we need to no longer offset the contact surface. This offset, it will include geometric and the contact offset, so this would double up the amount of interference fit we have. So I'm just going to zero that out to essentially run the same exact problem again. Kick that off and look at what the normal stress is in this problem this time. And it was 67.7, now it's 67.6, so that's a little bit closer to our hand calc, a little bit better answer, but not really by any significant amount. And if we zoom in down at this location again, we see that we no longer see that physical gap in there. The surfaces are touching line on line because we didn't offset the contact surface amount. So this is maybe a more realistic answer. Let's say the pin is modeled with its true diameter, it's modeled line on line, looks a little nicer. Results are a little bit more accurate, but really it didn't make any difference how we modeled this in either approach. They're both essentially the same answer. So now these results look very nice around the circumference, but if we take a look at this mesh for a second, since we are interested in stress and accuracy of the solution we're getting, we see that this mesh is lined up node to node, or the elements are lined up, same number of divisions around the circumference. Very easy to do in 2D, but if this was a 3D problem, that's generally a little bit more difficult to have happen. So I'm just going to change this mesh so that way they don't line up anymore. Right, see, now we get different divisions all the way through here on each side. So if we solve this problem now, and all the analysis so far that I've been running has been with lower order elements, which is a faceted approximation to the curved surface. You can see here that this one element is a straight edge. So we're getting a faceted representation of this cylindrical surface. And we look at the results now, and we see that they're quite poor. I mean, this is 108 KSI, and the results around the circumference are highly irregular, So we're getting, very sharp or high isolated stresses at those sharp points. And that's just due to the lower order mesh that we're using. So that's not the best answer to this problem by any means. You could refine the mesh, but it's probably not going to get all that much better. So one thing we can do is use some higher order elements and rerun this. And if we look at the higher order elements, they will have the mid-side nodes. They'll have curvature to them. So then it will represent that curved surface a little bit better through here. It's not straight anymore. And looking at these results, they're still not great. We're looking for 66 KSI at 77. The results are, still somewhat irregular as you go around the circumference there, although it is better. And you could probably refine the mesh a whole bunch more, and then even though they're not lined up node to node, you could still probably get a pretty good answer. And then I should also point out, too, that we do have some inflation on here. So these elements are refined, closer to that surface. So in both of these cases that I just ran, zoom in this way, the contact detection that we've been using, meaning that there's a contact element that sits on this face. And its detection method is program controlled, which defaults to on the Gauss point. And all that means is that across this one face of this element, there's a couple points on this surface that are looking to not penetrate the target segment on these other element faces right there. So that's the detection. It's still essentially like a point-to-surface type of a contact through there, which leads to some of this irregularity that we see around the results in the circumference. So there's another detection method that we can use, and that's called the projection, nodal projected normal from contact. And let me rerun this again. And what that will do is we zoom in on the mesh here. Again, it's going to take, let me get this. So it's going to take that one element, and it's going to take that whole segment and look to not penetrate this entire segment. So it's really segment-to-segment based contact. And if we use this contact, now you can see this result is 66.7. I think that's the best stress we've got so far in terms of accuracy. And it's also very smooth around the circumference, and this is a dissimilar mesh as well. So just showing that the difference in that contact detection makes a big difference in the results here. So let's go back to the PowerPoint now and just show these all side by side in a quick summary. The initial model was lower order elements, and then the mesh did line up, and we got something, reasonable accuracy, 67 KSI. But then if we make the mesh dissimilar with the lower order, it gets quite awful. And it gets a little bit better with the higher order elements, still not that great. But then we take the higher order elements and then use the projection contact, and you see that that's our best answer so far. So that's just illustrating some of the things related to accuracy at the contact interface. Now there was another problem that I wanted to show you quickly, that it's not an interference fit problem per se, but essentially it's the same to solve this type of a problem. So this is the model here. We have an O-ring seal, some type of gasket, and this could be, just pretend it's like some type of a case, and then the lid on the case. So we're snapping an O-ring in between two parts like that. And we want to solve this problem. So we want this seal to be loaded up in here, and maybe so that way water doesn't come in, or whatever's going on with this. So we set up some contact between this O-ring and this housing, and we just set that pinball radius to be larger than this physical penetration. That way this point down here realizes it's penetrated through this target segment at the beginning of the analysis. And there's no contact offset, it's just geometric interference. And we've also set to add offset with ramped effects. It's an option in here. So all that does is that at the end of the first load step, each sub-step, it's slowly going to move it up to the surface. And resolve out that initial interference. So if we looked at the results of that, we see that it does get squished in there at the end of the load step. And if I animate this, we can see what it did from the start to end. You can see it just takes that problem, and then just because of the contact interference, it just goes and resolves it out and puts it line on line at the end of the analysis. So this is pretty easy to set up and solve a problem like this, because all that you have to do is just hold these two parts in their closed position, and then just let the interference work its way out to load it up how it wants to. Now, you could solve this same exact problem in a slightly different way, right? We could have this case and its lid be open, right? And then we want to close them together and clamp down on this O-ring. We could certainly model this, and if we animated this case, you could see that it looks essentially the same, except you're just squishing it together. Right, so that's what's going on here. If we looked at the results between these two, let's just look at the normal stress in the vertical direction here. We're like at 328 psi. And we could go back and look at the stress in here, 327. So essentially the same exact answer. Right? We just solved this a different way. And if we looked at this in terms of how easy it was to converge, well, this model took 38 iterations to converge, resolving out the interference fit. And then modeling it this way, it took 42. So, it depends on your settings and things, but, this is essentially identical convergence and identical answer, but solving the problem two different ways. I will say, though, that solving the model this way is generally more difficult to get to converge, because we're taking this part with a displacement, driving it up, and holding this fixed. So there's nothing going on here, but this part initially there's a gap. So there's nothing holding this from moving off in rigid body motion. So we have to do some other things that prevent that rigid body motion. And in this case, on this contact pair, I just used some contact damping to resolve out any of that motion that may occur. So there's little things that you may have to set for the different problems, but it's not really a big deal. At the end of the day, you can get nearly the same exact answer. And if we just do one more thing, look at the normal stress, 328 max down here. If we looked at the contact results, contact pressure that's going on here, it's 345. So those don't match up, maybe exactly as we would like. They will if we refine the mesh some more. And you can see at the mesh here, we did use inflation, again, just to put some more elements near the surface and get a little bit better resolution there, but that could certainly be improved. And we could also look at penetration as well, since we talked about that in the beginning. So we have 0.1 thousandths of an inch penetration. We can look and see if that will change the contact normal stress and load that gets transmitted through here. So, all these things we can look at again. And then to say one other thing about this type of analysis, let's just say that this was a different problem. Now, let's say that this was a shaft, where this is the axis of the shaft, and this was a bearing up here. Right? So this is a 2D axisymmetric analysis. This is a radial direction axial. So we wouldn't be able to solve this problem right here the way that we just did, right, where we take and move this up in the radial direction. Because if we did this, if this was a shaft in the center line, you would have to be making the shaft diameter larger. Right? You'd be inducing a huge amount of hoop stress in here to try to preload and solve the model in this fashion. So if this was the type of problem that you're running, you couldn't run it or compress the O-ring this way. You would have to model it this way, where the shaft is the right diameter, the bearing's at its right diameter, and then you can have some interference fit in there and then just resolve it out, based on the contact. And there's, some other ways you could probably do this, but just showing that in this case, this would be an easy way if these were an axisymmetric model to preload this gasket in there.